the UH Energy Electric Vehicle webinar series. Today we will be discussing electrification of rail and sea transportation. So my name is Andres Bryan, and I'm a current senior biomedical engineering student here at the University of Houston, and I will be the moderator for today's event. Before we begin with the event for today, I want to take a minute to thank our partner Evolve Houston, as we're very fortunate to have them working with us to help spread awareness about electric vehicles. I'd also like to take a moment to remind everyone of our next webinar on March 10th, where second-year Masters of Environmental Management candidate at the Yale School of Environment, Bridget Gilmore, will address an analysis over vehicle miles traveled and the electrification potential of the Houston region. To learn more about the electric vehicle webinar series and our past webinars, please visit the UH Energy EV webpage using the link in the slide. So moving forward, we will have the Q&A session at the end of the presentation, so please hold on to all your questions until the end. That being said, we will utilize the chat function throughout the presentation. So if you have a question, you can go ahead and send it in, but just remember that at the end of the presentation, I'll take note of whose question went first, and then I'll be able to ask Dr. Krishnamurthy the questions. So without further ado, I would like to introduce Dr. Harish Krishnamurthy. Dr. Krishnamurthy received his Bachelor of Technology degree in India in 2008 and his Doctor of Philosophy degree from the Electrical and Computer Engineering Department at A&M in 2015. From June of 2008 to July of 2010, he worked as an electronics engineer with GE Energy and received the Lean Six Sigma Green Belt certification there. From April of 2015 to July of 2017, he was an electrical engineer with Schlumberger and had the opportunity to work briefly with Ford and Google. Since August of 2017, Dr. Krishnamurthy has been working as an assistant professor in the Electrical and Computer Engineering Department at the University of Houston. He has published over 50 IEEE conference and journal papers and has one granted patent. He has also co-authored a book chapter under IET. He is a senior member of IEEE and the chair of IEEE Pell's Young Professionals Group. He is also an associate editor of the IEEE Transactions on Power Electronics and has many research interests. Some of these include high-density power conversion, statistical methods for improvement in quality and reliability of power electronics, advanced power electronics, and control for applications such as electric vehicles, renewable energy, and 4G/5G envelope tracking. So electrification of automobiles and aircrafts has gained a lot of attention over the last few years, mainly owing to the higher efficiency and lowering the carbon footprint. Transportation electrification extends even beyond that. There have been several developments in electric railways and ships, which play a crucial role in reducing carbon emissions. Electric rail recently got even more attention in the US since the high-speed train between Houston and Dallas received federal approval. It is estimated that the rail and sea transportation together contributes between 3 to 5% of the total carbon emissions due to human activity. This webinar will discuss some of the trends and advancements in the electrification of rail and sea transportation, along with a broadened view of the different electrical systems used in these applications.
Hello everyone, my name is Harish Krishnamurthy and I'm an assistant professor in the ECA department of University of Houston. Today I'm going to give a talk on electrification of rail and sea transportation on behalf of UH Energy Electric Vehicle webinar series. And thank you all for joining today. As you all know, electric vehicles in terms of automotives and aircrafts have been very popular, and many of you are up to date with such developments because they are in the news every day. But there have been a lot of advancements in the areas of rail and sea transportation. I will be covering some aspects today, mainly with regard to power and energy. So today's agenda is to have a brief introduction about electric rail and ships, and we'll be going towards electrification of railways, and considering when we are in Houston, we'll cover some aspects of metro rail, and then the high-speed rail, which we are all long awaiting for between Houston and Dallas. Now then we'll go towards electrification of ships. And we'll briefly talk about commercial fleet, but then there will be some more additional features to discuss on the naval fleet, and then we'll have a summary. So with regard to electrification of railways, so as like many of you might know, global market for railway electrification has been growing significantly. Now it is expected that it's almost close to $14 billion right now, and of course, even with the COVID pandemic, things have slowed down a little bit, but still, it's bound to come back. This is in terms of the railway lines. At the same time, the global electric locomotive market size is projected to be about $8 billion in 2023. So there have been a lot of improvements on both fronts. One is electrification of the line, and then the electrification of the locomotives themselves. So the total market size of locomotives is projected to be somewhere around 6,000 now. Now, in terms of railways, there are three major types of trains or rail transportation that we are aware of and popularly looked into. So one is the urban vehicles like trams and metros. So most of you should be aware of being in Houston area. Then there are regional and commuter-based rail transportation, and then there are high-speed railways, which again is being planned pretty soon. In terms of the developments in the Houston area itself, the first one which comes to our mind, which has been there since 2004, is the Houston Metro Rail, and it'll be a fun fact that Houston Metro Rail is the second most traveled light rail system in southern U.S., which extends from Texas all the way till Florida. We are just second only to Dallas Metropolitan, and there are about 37 Siemens S70 metros and about 39 CAF USA vehicles, and some of the more recent ones are the CAF ones. So the overhead lines which actually kind of power these metro rails, they are usually 600 volt to 750 volt, and then that voltage has to be kind of transferred within the machine, and that needs to drive the tram. So basically each of these tram, like typically some of the metro rails which actually travel from, let's say, the north-south direction, is typically about size of two trams. Some could be just one, and roughly each tram will be about 80 kilowatts. So that's kind of lower than that of a car, an electric car, but basically with the rails and the speed at which they travel, usually this power is sufficient. Now, the exciting aspect, which is kind of which we are all eagerly waiting for and planned for 2026, is the Texas Central Railway. So that's the high-speed train which connects Houston and Dallas via College Station, and the model of that high-speed train is based on the N700 series Shinkansen, which is called the bullet train in Japan. So they travel up to 205 miles per hour. So they are really a bullet train, right? So basically, Houston to Dallas in 90 minutes. Whether we travel by car, unless we really, travel at very high speeds, we won't be reaching Dallas from Houston in 90 minutes. So this is supposed to be an all-electric system with several steel wheels and several rotors. So I think we'll watch a small short video to know about this bullet trains.
Japan, an ancient nation that has helped to engineer the modern world. High-rise megacities sprawl along the country's coast, separated by soaring mountains. One machine links these far-flung cities together in super quick time. The N700A Shinkansen, also known as the bullet train. This is a train like no other. Its aerodynamic nose pierces the air with hardly a sound. It glides on 128 solid steel wheels. And an ingenious system allows the train to tilt into corners without losing speed. 128 air-powered brakes can bring 700 tons of train to a complete stop. And two finely balanced spring-loaded arms deliver enough electricity into the train to power 40,000 homes. This machine is built for one purpose: to carry more people more quickly than any other train on Earth. The bullet train has many smaller engines that are spread throughout the train. 56 electric motors deliver more power than 75 Tesla Roadsters. 2 spring-loaded arms called pantographs push against 25,000 volt overhead cables to provide the electricity to get these motors running. Gears crank up the turning power and drive sets of hardened steel wheels to over 1,800 revolutions a minute. Together they power the bullet train to 180 miles an hour in a mere 3 minutes.
So as you can see, these bullet trains are really huge machines. So if you notice this, it's roughly about 17 megawatts of power in one machine, and with a that entire bullet train with a seating capacity of about 1,300. Um, so basically, we have a 25,000 volts AC voltage, and typically single phase, and you need to convert this very high voltage into all these tiny rotors that they mentioned, like tiny motors, about 56 or 58 of them. Again, that depends on the number of cards per train. So these are very high power machines. So again, considering the extent of electrification required, we need to make such systems small enough and then efficient enough for safe and future transportation. So so what are all the essential electrical components which kind of form inside an electric train, especially the locomotives? So as you can see here, from the pantograph, you have a 25,000 volts coming in, and just for safety purposes and or to step down the voltage from such high voltage onto a relatively lower voltage, which again can be kind of fed to all these wheels here. So some of the essential components in the path will be the transformer, as we discussed, and then there will be a series of power electronics conversion systems, and then there will be a motor drive inverter, and there could also be some aspects of energy storage. Because let's say if the power goes away, you don't want you want the entire train to be at least moved to a safe location. So all these are essential components of an electric locomotive and train overall. And as you saw in the high-speed rail, actually the good thing is the rotors and then the pantographs are kind of distributed across different different cabinets, right? Different modules of the train itself. So the distributed power will probably kind of make it more reliable. So as we just discussed, the 25 kV or 25,000 volts, that has to be stepped down to a relatively lower voltage. So some of the reasons for that is with regard to the power conversion systems, these individual switches, as is shown here, these switches are currently rated for much lower voltages. So 25,000 volts rating seems it's very high. So if we step down that voltage to a relatively lower voltage, it will be possible to use relatively smaller voltage rated switches. And then like after something called a rectification stage, there is an inversion stage where this single phase 25 kV AC can be converted to 3-phase machines. So usually it's much more easier if you split the different number of machines instead of just one or two. If we have this 56 of them, as you saw in the video, and all these machines are 3-phase machines. Again, that makes the operation smoother and basically that kind of follows the technology that we have available. Now, another option as compared to the one that we just saw before is like, of course, the transformer stage is similar. Again, the transformer has to be designed for a relatively lower frequency. That is, in the US, it will be 60 hertz, and let's say in Japan and many parts of Asia, that's 50 hertz. So you can actually split this transformer windings to multiple secondary windings, and then use a lower power converter stages for each set of traction motors. So that's another option. So basically, like, different companies will come up with different architectures, and let's say if you want to kind of have a single pantograph and then have the remaining power to be transferred to different different bins in the train separately, then this architecture may be suitable. And now, especially with developments in the power electronics technology, of course, as I mentioned, 25 kilovolts is still very high, but at the same time, there have been silicon carbide based MOSFET switches which are rated for commercially available 3.3 kilovolts is very much available now, or 3300 volts, and it's kind of increasing. And in terms of research phase, 10,000 volts rated devices are also becoming increasingly available. So instead of using so as you see here, compared to the previous stages, you don't need to place a conventional low frequency transformer up in the front. Rather, you use a series stacked, one top of the other, series stacked power converters, which together can handle the 25,000 volts which has been applied. And at the same time, now you use something called an isolated stage of power conversion, where instead of a low frequency transformer, you can use a medium or higher frequency transformer. So instead of 50 to 60 hertz, people have been looking to go towards anywhere from the upwards of 500 hertz, 1000 hertz, and maybe in the future we'll probably try to go towards 10,000 hertz. So and then after that, the collecting the voltages which come out, and then putting together to form towards an inverter and traction motors, that remains pretty much the same. So one of the major advantages of this structure is the higher frequency transformers, as I mentioned, like medium or high frequency transformers. They are usually much smaller than the line frequency transformers, because of the operation at higher frequency. So this structure can be made at least 40 to 60% smaller than the traditional transformer based circuit designs. So some companies have been already looking at it, and such benefits are really important, and they can be made more like similar or more efficient. Some of the challenges with such a design is you're making the power electronics switches handle the front side of the system, so you may tend to have more noise issues. But again, there have been solutions which actually take care of that. So one type of transformer which can actually operate at a higher frequency, let's say 500 to 1000 hertz, is using amorphous silicon steel based transformer cores. So all the huge transformers that you see around, like when you are on the road, like the substations and so forth. So these transformers are typically made with silicon steel. But let's say if you move towards an amorphous steel based transformers, you can actually make the transformers smaller and much more efficient. So ABB is one of the companies, they already designed such transformers. And I believe many companies are looking to adopt this technology even for electric rails. Now, coming to the auxiliary power of metro rail. So, of course, we started with the high-speed rail and then metro rail. So, as we discussed on the metro rail, maybe the total power required for each bogie that could be about 80 to 100 kilowatts. But as you saw, instead of 25 kV AC, we only have options of 1500 volt DC or a 750 volt DC or 600 volt DC. As we discussed, the Houston Metro is usually 600 to 750 volt DC as per sources online. So for such systems, how do we employ the power conversion systems, right? So basically, instead of a rectifier stage which converts the AC side to a DC inside the train, here the input is already DC. So the interesting aspect here is, of course, with a 600 or 750 volts, you now have a DC to DC isolated converter stage. That's mainly to kind of make the all the centralized systems operating inside the metro rail to kind of feed off from the same DC bus. So of course, this particular converter will also be an isolated converter, but considering 180 to 100 kilowatt, there already is a well-established technology for isolated like DC to DC converters, which use high-frequency transformers. So that is typically being employed, and then you already have this backup battery system, which will be connected to the you can consider the center as a DC collection point where the input side converted, and then the battery side, and then the inverter all are tied together. So from this DC feed, like just like in your electric cars, you have a DC bus which kind of feeds onto an inverter, and then the wheels are driven using that inverter. And then of course these wheels, these inverters can be variable frequency drives, and there are all these techniques which are used to improve the efficiency of the motors. And this these battery systems itself, their voltage has to be adopted, so that's why you have a DC to DC converter here. So basically, even if the battery voltage changes over life, your or even charging discharging, your DC to DC converter will take care of it. So basically, whenever you need additional power to the load, your battery can feed add to the power coming from the pantograph, and if there is sufficient power already available, or if there is a regenerative system in place, then the battery can be charged either through the main power or the regenerative energy. So I hope I gave you an overview of the different electrification aspects of railways, kind of more like interesting for the Houston audience. Now we can move towards electrification of ships. So again, like as we saw in the railways, electric ships are also very very large power systems. You can consider each of these large ships as a microgrid by itself, right? So several times, like you have no other power source, so you are out in the ocean, and then you are all left to whatever is available inside the ship. So last several decades or maybe centuries, typically steam plants and mechanical propulsion kind of dominated all the different types of ships, whether it's merchant ships, cruise ships, or military ships. Now, currently, many of the technologies are slowly trying to adopt electrification. So some of the difficulties are, like, especially with if you want to have a purely electric ships, then you need to store energy in huge battery banks and move from there, right? Like basically, if you want to make it all electric, so that's a big challenge. But what is expected now is probably you can still generate the electricity using diesel generators, or but and even the propulsion is mechanical. No, actually, the propulsion can be either mechanical or electric. So depending on what type of ships that we are looking at, so here the cruise ships have electrical generators and electrical propulsion. it's becoming more of a norm. But going forward, even now, basically several of the military ships are trying to go towards much more electrification to improve different dynamics, which we'll talk about in a few minutes. So basically, the future possible scenarios, just like electric cars or aircrafts, we are actively looking into complete electrification, including from the generator side all the way to the propulsion and any of the intermediate loads which are there in the system. So what are all the main advantages of electrification? It's much more easily controllable, start, arrest, and speed variations. Electric motors will offer more flexibility. It's much more it's possible to improve the efficiency much more, which actually reduces the fuel consumption and the carbon emissions. Even with I think anywhere from 3 to 5% of the global carbon emissions are due to the sea transportation. So basically, if we significantly reduce the fuel consumption, we can kind of help with that as well. And with the electrification, as you know from electric cars, the vibration is also reduced, so you tend to have a higher comfort, and you can have a much higher level of automation in electric ships. Now let's take a typical example of a commercial ship in terms of the specification. So let's say if you have 142,000 tons with let's say about 5,000 people. So such a ship will need roughly about 70 to 80 megawatts of power, right? So that's usually the cruising, that's the requirement for cruising, and then the auxiliary supplies and all put together. You need a lot of electric power, and many of these, the power distribution is usually in AC, 11 kV or so forth, right? And then as you can see, like some enormous numbers, right? 4,000 kilometers of cable length, and then 23,000 circuit breakers. So as you see, even a cruise ship is an enormous machine, and with very hungry, power hungry systems installed. And of course, to drive such a large equipment, you need such a high power. So how are they usually laid out? So you have multiple diesel generators. They could be placed at different points strategically. I'm not an expert on the mechanical side of things. So basically, just to make sure, even if one of the diesel generators has an issue, others should still be able to help you safely maneuver any of the difficult situations that we face. And then you have these propulsion motors, which again are derived from the main bus bar, and so it's here shown as 17 megawatts for each propulsion. And then you have all these air conditioning for the cruise ships, and thrusters, and any type of entertainment. So all these will add to the required power of the entire ship. Now, I'm moving on to the naval ship architecture. So even with, as we saw, right, even with the cruise ships, basically we are moving towards a slowly moving towards a DC architecture. So instead of 11 kilovolt or 11,000 volt AC, now we are trying to move towards medium voltage or high voltage DC, which again will be anywhere around 6,000 volts to about 12,000 volts and so forth. And the military ships and naval ships are actually leading the charge. So what are the benefits of moving from an AC, even high voltage AC power distribution architecture to a DC architecture? So the main benefits are, as we saw, there are 4,000 kilometers of cables, right? So once you let's say when you actually pass AC, the line inductances, which will also play a part in the net power flow. And what happens is these inductances will need to be we called reactive power. So the more inductance, the more the higher the frequency of AC, basically we'll tend to have that there will be more reactive power, which will kind of contribute towards the overall loss, because the net current to transfer the same amount of active power is actually going to be higher, and then that actually leads to a higher transmission or distribution loss. So moving towards DC, basically the inductance almost, except for the transient conditions, the inductance will not really come into play in the transfer of power. So basically, and that can really save on a lot of losses, and then improve the energy efficiency and reducing the consumption. So at this time, basically the medium voltage DC, that is MVDC architecture, considered is more of a radial architecture in case of several distributed microgrids and so forth. So different power requirements, generator is the generator. So the difference here, compared to an AC architecture, is basically from the AC, which is generated by the gas turbine or a diesel generator, that needs to be rectified, and then the interface with the common MVDC bus. So you can see there's a main generator, auxiliary generator, and then the different loads. In case of naval ships, there's of course the propulsion and propulsion motors, but again, you need to have so many other aspects like radar technology, weapons, and pulse loads and so forth. So this is the architecture that have been looked at so far. But basically now the problem is that if you have some breakage in one of the areas of the radial architecture, the others will lose power. But so that could be very detrimental when you're either fighting a war, or that's even when you're stuck in the middle of the ocean. So now the emphasis is trying to make it a more zonal design, which means that the entire ship, you divide different sections of the ship into, each section will have probably a generation stage, and maybe a part of energy storage, and several loads associated. And let's say, even if and of course they'll have their own associated software and manpower. So let's say one or multiple of these zones are damaged, there is still a way to transfer power from one side to the other through other means. So that's a zonal architecture. So it is envisioned that make the survivability of the ship as an open loop design process, rather a closed loop design process. So here is a top view picture of the zonal architecture that we just discussed about. So let's say if there is some sort of a damage, could be during a war, or it could be a cyber security threat or something like that. So basically, if zones 3 and 4 are affected, you should still be able to transfer power from let's say zone 1 or 2 all the way to 5 and 6. So some part of the machine, the entire ship, should some parts of the ship should still work, which can really be beneficial in a war scenario. So this is more of a detailed picture of how things can be interconnected. Again, this is the different zones that we were discussing about. Now you have main AC generator and some aspects of auxiliary generators connected here. There are multiple auxiliary generators, and then on the left you have an energy storage. And then on the right, there are these pulse loads, and so basically the different types of loads will be distributed strategically. And then there is an immense interest in the Navy to actually look at what could be optimal designs for different types of ships. A destroyer will be much different compared to an aircraft carrier, right? Aircraft carriers can be a kilometer or more longer. And so for each type of system, there is an immense interest in understanding the unique the challenges coming with the different types of loads, and how to enable the different zonal architecture levels. Now, So there are other challenges as well. So basically, of course, if the more we progress in technology, we want to integrate more and more. So some of you probably would have watched these cool videos on these modern laser power weapons, right? Like basically you just like emit a high, like very high energy beam of light, and then it destroys enemy weapons and so forth. So these are called pulsed applications, right? So basically, the more technology comes in, and then there are more things to do with available power, and basically like the requirement for modern naval electric ships or naval fleet have increased significantly. But if you look at on the x-axis, basically in terms of the power, of course, we are 7.5 to 9 megawatt installed power, 12 megawatt installed power, and then we are trying to move towards a 75 megawatt geared propulsion, of course. But then there is a question here which comes in, like, probably what if we cannot make that happen, because we cannot keep on increasing the available power at the same time, right? So whatever is available, how do we use it strategically, right? So basically, that's what it's shown as, like, it deviates from the traditional path of, how do we increase it. So for that, actually, instead of like just looking at it from a power perspective, now there is an increasing interest in looking at it from an integrated power and energy system perspective. So what that means is, of course, in terms of the different types of loads, you have several loads like propulsion, which is needed, like, frequently, right? Like when something is moving, you need that propulsion to continue. But then there are things like, rail guns or radar systems, or some of those weapons where you don't need very continuous power. Rather, you have these pulsed power, and then if you look at the average power, they could be like much lower. Moreover, depending on how much ever is available, you look at different scenarios. Whether, let's say, you're not moving, then you have more available power which can be used for probably kind of using more number of weapons. So rail guns are other very interesting type of weapons which are increasingly being used, and I'm sure you would have all heard of these like hypersonic weapons and so forth. Now, so this integrated power and energy systems, as you see here, like basically we have DDG 1000, which is it's a more traditional method, which is looked at it from just the power system perspective. But then now we are adding energy storage to take care of the power and energy perspective, and then we are able to kind of put in more advanced control systems. And then here, in terms of the IPES architecture, you can see the zonal architecture again, what we had discussed before. So what are the tactical advantages? Like basically giving more flexibility, survivability, and then giving more efficiency. So basically adding a lot more intelligence into the ships compared to what's available traditionally. So here it just demonstrates the different types of loads which are available. So basically, like what we have right now in terms of available power, and then basically like we take step up approach, like every time we, of course, the available power, that side, that's generation side also improves significantly. But then the demand for more and more power, actually that's more like an exponential growth. So at some point it has it cannot be met, right? Like, so basically we need to look at better ways of adapting to the existing system. So on the right, what you see is, basically you add a constant power with a pulsed weapon demand. And if you have energy storage like battery or some supercapacitors at strategically located places, you will be able to actually, just take that pulsed energy from these battery systems rather than taking it from the generator. So that will actually significantly improve your utility of all the generators, and actually also let you take actions as needed. So, so here again, it shows a similar scenario where you have like radar systems, rail guns, lasers, and all these are pulse loads, and what happens to the voltage on the, the grid voltage when each pulse load comes in. So if you add some sort of an energy storage, you can smoothen this up a little bit more, because if your DC bus is changing rapidly, it can lead to so many different problems, because all the major loads are being absorbed from there. So again, these are all technologies that are being looked upon as we speak. So one more aspect of this entire electrification of ships is, as we saw in the zonal architecture. Let's say if the power, if there a couple of zones are affected, what happens to the remaining zones? So basically, you can you can like divert power from one part of the ship to the other. So basically, that requires different power electronics converters, right? Like basically, the power converters are the ones which transfer, which kind of play a part in transferring each to the other. Now, there again has been an increasing emphasis on making those power electronic modules as more of a building blocks, which can be kind of quickly set up and then added in series and parallel. So we call it a power electronics building block, where each part of the converter system has can take care of its own intelligence and controls and switching, and then let's say you interconnect a few, put them together, they have enough intelligence to work together at the same time. So there are, like, again, looking at multiple building block control layers. There is aspect of actually going from the bottommost layer, where you look at every capacitor or a resistor, or the mechanical design, the thermal, and all those, and then going all the way up to the system, which is kind of controlled at the ship level, using like SCADA or other GUI. So that has multiple layers of operation. Basically, like you need to look at how each switch in the power converter behaves. Of course, that doesn't have to be communicated all the way to the top layer of control. Rather, there should be enough actions which can be taken at the individual converter level, or a certain module level, and such actions can, like the gist of the actions can be kind of communicated to the next layer. So basically, from each module, then you connect this group of modules and make a whole converter. So that converter control can be the next layer, and then again the overall application control, and then the system control. Again, this slide shows the different time scales which are in effect. Like when we talk about the individual power converter switches, the switches will operate at the speeds of several megahertz. So basically, we need to react very fast to those. So there have been researchers in government, industry, and academia who are looking into each part of these complicated control layers. Now, as we saw before, like Virginia Tech and ONR have been looking at this power electronics building block. So basically, how you can visualize is, like you make each building block with the basic circuits. So as you see here, it's a common circuit which is used heavily in power electronics, and then it has all the required control and gate drives and system control all kind of allocated. So imagine, let's say each is rated for, let's say, 1000 volt DC, and let's say 100 kilowatt power. So depending on the net voltage required, you can actually stack each of them in series, as you see here, like, depending on number of voltages, and then depending on the total power required, you can connect more and more such strings in parallel, very similar to solar strings and panels, which are being done right now. So this is a very interesting architecture, and then like for electric ships especially, such an architecture is increasingly being studied. So here are a peek into like what all will be inside such a module. Like each module will have a very complicated set of control and like very advanced devices which actually can take care of different scenarios if given the command, right? So of course the net bus, like the voltage, if we need like a 10 to 12,000 volts DC bus, we would need like very high insulation capabilities and so forth. So basically, just to kind of go over all this, so we actually went from a very conventional mechanical system-based electric ships all the way to very detailed configurations of electrification. So basically, like these are all the different technologies which are increasingly being explored in electric ships. So to summarize, increased electrification in railways and ships provide a lot of new opportunities for researchers as well as even the participants in these areas. So basically, like overall, the power consumption and the flexibilities are being improved, especially for cases where you have more than 10 megawatts. And like reduce environmental burden, that's one of the main significant aspects that we are looking at, and again, like smaller size for better maneuverability. Electronic transformers, as we discussed, again, like using a medium or high frequency transformer instead of the large low frequency transformers is again it's not just in electric vehicles but also for grid applications. That's heavily being considered because it's becoming more and more viable. And one thing which we didn't really touch upon is like once we have more complexity in the system, there's again like options for more things to fail, and then there is a growing trend of data-driven approaches and automation for kind of predicting how the life and behavior performance of each system is going about. Now, finally, again, like in large systems as well as in grid-based applications, machine learning-based digital twin and design optimization for the overall system are being kind of embraced a lot. So basically, this is to understand, like even before taking an action, the digital twin or the software model of a practical system, so you can understand how how the system will behave at a certain adverse condition, where the system will break or not. So that's a very unique prospect which is going on. So overall, electrification, I feel that it really will improve not just the traditional electric vehicles, but also mass transportation. So please stay tuned. Before we go, I wanted to just bring to your attention the power and energy related courses and degrees that we offer at University of Houston. So basically, we have two certificate programs, Power Electronics and Renewable Energy, graduate certificate programs, and then we have Power Systems and Smart Grid. So these courses are all completely offered online. We do have a master's degree program with specialization in power and energy. Basically, we want to provide an opportunity for people like all the industry folks who cannot really travel to campus. At the same time, you want to take up a course, and basically now at the comfort of your office or your home, you can still take all these courses. And we do offer a distant PhD program as well. So again, for people who have considerable work experience, there's a reduced course requirement for experienced engineers. And if you have any questions, we'll be glad to provide you answers with. And we wanted to touch base with the Greater Houston area and even beyond to kind of establish our program further. So with that, I really thank you for your attention. I'll be happy to take any of your questions. Thanks.
Thank you, Dr. Krishnamurthy, for that really informative presentation. We're going to go ahead and jump into the questions because I've already gotten a couple. So the first one would be, what are the prospects for converting marine fleets to nuclear power, like warships? The Savannah 40 years ago was nuclear. Can there be a direct conversion from fuel oil?
So actually, that's a very good question. So with nuclear fuel as such, we should be able to get very high power density for several types of vehicles. That's actually a very good prospect. But it's just that first aspect is the cost. So I think with nuclear fuel that will really increase the cost. Second is the safety. So for applications, especially in the defense sector, such an approach should work fine. But for commercial, especially with thinking about cruise ships, where the travelers will be very much critical about the safety. So I think there I don't know how much of that will survive.
Okay. Another question is, the ships that you described have onboard gas turbines or diesel engines to generate power. Is there any future potential for carbon-free battery-operated ships?
Yes, I think there is a lot. So the only thing is if we have to consider pure batteries alone for a very long distance cruising and at that power, it's going to probably take some while before we can design such a system. Of course, now we are successfully doing the same for electric cars, and I think increasingly we'll see that once the battery technologies have also improved significantly, I think we should be able to get to at least in the relatively smaller ships, we should be able to get that going.
Okay, and is there any use for electric battery storage in any of those applications?
Yes. Definitely for all the applications. In fact, if you see one of the slides where we discussed about the DC metro rail, for example, right? Even that has batteries. Then, in ships as well. What if there is some issue with the generator? We need to have batteries to provide backup, at least, if not more. And once we start looking into varied dynamics of these ships and other vehicles, then having a battery or a supercapacitor, these will really help reducing the overall size of the generators as designed.
Okay. Another question is it feasible for electrification of long-haul freight trains?
I think so. I think if you look at several countries, I I would think even in the US, at least some parts it should be fully electrified. But in several other countries, very long distance freight trains have also been electrified. So I think it's just a matter of time.
Okay. Eric Pratt's asking, is the USS Ford aircraft carrier with the EMALS electromagnetic aircraft launch system a high power use and control then can be presently made reliable?
So, in terms of the specifics of the system, I may not be that knowledgeable, but one thing I can say is with the very high requirement of high energy for a very short time, we we would definitely want to look into energy storage with batteries and as well as supercapacitors in working in conjunction with the traditional source of generation. So I think with that we'll be able to, just one more aspect apart from just the availability of power. It's basically the placement of all these different types of sources. Where do we keep them? Because if the battery energy storage and the supercapacitor, they are placed very close to the loads, that will actually provide all the sudden requirement of energy will be very close to the load. So it will have much lower impact on the distribution grid, and you won't have the voltage of the MVDC distribution bus getting lower to an extent that it can affect other systems.
Okay, thank you. Let's see. I think Jack's asking, are we looking at hydrogen fuel cells to generate the onboard power for trains? I think Germany is looking at this.
Yeah, I think that's also a very good idea. So I don't know if it is to believe, but I was looking at some articles which were talking about whether it is more economical to have a pantograph based line connection for electric trains, or should we have onboard like fuel cells or batteries. So a lot of places, like, the studies are finding it may be more economical to have this pantograph based thing, where, like, there is a connection at the top of the train, and you directly connect to the power lines. And so I mean, I don't know exactly if that is true in all the cases, but definitely, having with hydrogen storage and fuel cells, they are, like, they are starting to get more and more interest now, because now there's another point of view with so much of electric vehicles, and a lot of battery systems being used. Can we get all the batteries in time? And second thing is recycling all these batteries. So I think personally the best approach is to start bringing more such like sources into picture, like, fuel cells and others together. I think it'll be a much better prospect.
Okay, yeah, I agree. Brian Lee is asking, with increasing ship generator capacity, can we expect to see an increase in ships in port selling back to the grid in larger numbers?
So ship so it is more of a strategic question. So basically, like, of course, when we have when the ships are on like on the port, I think it's actually a very good idea to send some energy back to the grid when needed. But
Yeah.
most of the time when the ship is sailing, of course, we cannot do that, right? So it's different from what we have with electric vehicles, where we expect the electric vehicles to be at our home and connected to the grid if possible in the night time. So we roughly know when we can actually, I mean, it's still complicated, but at least the cars will be at home most of the days in the night time. But for ships, that planning could be a very interesting thing. But it could be a very different market. So letting the ships to feed power back to the grid, that's actually a very good market.
Yeah. He said he just messaged another message, and it says through high voltage short connections.
Sorry, could you repeat that, please?
Yeah, he just added on to his question saying through high voltage short connections. To clarify that.
Okay, so that is that will be a little you know technical aspect there. So if the ships are MVDC, the traditional high voltage AC systems are, high voltage systems are still AC on the shore. So we will definitely have to have some sort of a converter to kind of convert that. So we'll have to evaluate if there is, like, if there are several number of ships which are at the port, and if there is always a requirement for power being transferred from the ship back to the shore, I think then we can make such a converter viable. So it will come down to the cost and implementation. I think the technical aspect of, we are almost ready with that. We should be able to achieve such a design when needed.
Okay, great. Another question is, how can Houston be, what's it called, improved by having more electrification of their rails? What would be some of the benefits that you see that would make Houstonians take the rail more instead?
Okay, that's a tough question. So I think with more electrification, I think especially with this high-speed rail, if we can get from Houston to Dallas, which is a very busy corridor, right? Like if we can get from Houston to Dallas in 90 minutes by train, that time is probably the most important factor. And even with our regular metro rail, I think it's a time. Time is one of the factors. So wherever, especially like I have been on those trains. So if we can go from the medical center to downtown, I think metro rail will be the fastest way to go, considering all the morning traffic. So ultimately, when with more electrification, um, uh, uh, the main challenge there is how do we reach more locations in and around Houston area, and if we can touch upon more areas with electrification and then have such rail systems, and if they can also be very safe, then I think personally I would be very interested to take that.
Yeah, I agree. I'm interested in that too. Well, unfortunately, it's almost 2 o'clock, so we're gonna have to bring the Q&A question to an end. But I would like to say a big thank you, Dr. Krishnamurthy, for such a wonderful presentation, our partner Evolve Houston, and everyone in the audience for attending this event. Please make sure to join us for the March 10th webinar with Bridget Gilmer talking about vehicle miles traveled and electrification potential for the Houston region.
Thank you so much. It was a pleasure to be with you all today. Thank you. Enjoy your weekend.
Thank you.
And stay warm.
Yeah, please stay safe. Don't get on the roads on Monday.
Yeah. Thank you, guys.